All right, welcome everybody to the first meeting of TAPIRS. So we're very happy to have Eric Ramos speaking today, and he's going to tell us about the graph minor theorem and graph configuration spaces. So go ahead, Eric.
Awesome. So hello everybody. Thank you, Andrew and Jenny, for inviting me to speak, and it's really quite wonderful to see many of you. I feel like I haven't seen you in a long time. Okay, so let's just start with just some basic definitions here. So definition. So for this talk, a graph is a connected and finite CW complex of dimension at most 1. So just, I guess, full disclosure here, what I'm about to say probably doesn't work if you work with infinite graphs. And this is a consequence of the fact that the graph minor theorem is probably false, or at least independent of foundations if you work with infinite graphs. So graphs here are always going to be finite. So to remind all of us, a minor of a graph G is a graph G prime obtained from G by a sequence of edge deletions and contractions. So I guess I won't super formally define what a contraction is, but I think the only point of confusion I've run into in the past with audiences is you're not allowed to contract loops. So a contraction is by definition a homotopy equivalence. You are taking an edge, or rather some forest inside of your tree, and collapsing each of the constituent trees down to a point. So for example, maybe something real simple. So like we can have a graph like this. Maybe it has a loop. And this will be a minor of the graph that looks like this. Sorry. So here I have, let's say, deleted this edge, and I have contracted 2 of the 3 edges of the triangle. Any 2 will give you the same graph ultimately. So yeah, I've contracted the 2 purple edges and I've deleted the red edge. Okay, so the idea of graphs and graph minors have been a pretty major part of graph theory for at least the last 50, 60 years. It's been decades. Perhaps the most popular, just like pop math type of place that they show up is in the following theorem of Kuratowski-Wagner. Independently, Kuratowski and Wagner proved this, which is the fact that if G is planar, if and only if it does not contain K3, 3, or K5 as a minor. So this is the characterization of planar graphs. This is super famous. I'm sure everybody here knows it. What a lot of people I've discovered don't know is that Kuratowski-Wagner is in fact one very special case of a theorem that's like almost infinitely more general. And the more general theorem, called the graph minor theorem, says the following: given if S is any set of graphs, then S contains finitely many minimal elements with respect to the minor order. So the usual kind of combinatorics of posets, there's like a million equivalent ways to state this. For instance, in any infinite collection of graphs, you can always find one which is a minor of another. Or if you take any minor closed property, then there exists a finite list of forbidden minors which characterize it. So Kuratowski-Wagner in particular says that there are these two graphs that characterize planarity. And in fact, that's something that's general for any minor closed property. So this is the graph minor theorem. This is proven by Robertson and Seymour over the course of 20 years. It's pretty incredible because it was 20 papers labeled the graph minor, or rather the theory of graph minors part 1 through part 20. They were published somehow in order, all in the same journal over the course of 20 years. So it's like that, but even if the results were not good, that would be an incredible accomplishment. But of course, the ultimate result here is pretty incredible. Yeah, so kind of the idea, so the main idea.
I have a question, sorry.
Yes.
Yeah, so I guess this question is not that fair, but is there any reason that I should be expecting this to be true, or is there like some succinct idea from the 20 papers that you can say?
Yeah, so it's hard, sorry. It really is quite surprising. In fact, like if you generalize this even slightly, for instance, you might ask like, oh, is there a matroid minor theorem? The answer is no. The analogous thing is false. If you kind of alter the minor relation in some slight ways, is it still true? No, it's false. So it is actually quite miraculous that the graph minor.
I think one thing that might be worth saying is that it was so the special case of trees was known long before this, and I think
Yes.
sort of motivated. Like I think the graph minor theorem was a conjecture based upon Kruskall's tree theorem, which was maybe the special case of trees, which you can prove like in a page and a half. It's not that hard.
You could prove in a page and a half, but it was Kruskall's tree theorem was conjectured and unproven for like 2 decades before they managed to figure it out. The page proof is quite like clever and subtle. Sorry, I don't know if you can hear that. My neighbor is getting a tree cut down because it's Oregon. Okay, all right. Okay, so the main kind of goal of this talk is to categorify and apply the graph minor theorem. Okay. Right. So the first then challenge is somehow to actually create a category whose morphisms in some sense encode the minor relation. And this is kind of the first technical challenge here. So let me just say definition. The graph minor category fancy G is that whose objects are graphs and whose morphisms are what we call minor morphisms. Okay. Yeah, so the definition here is a little bit technical and kind of combinatorially fraught. I'm going to opt to not give the precise definition of a minor morphism. Suffice to say, however, that e.g. The morphisms are in some formal sense built out of deletions, contractions, and automorphisms. Okay. If I have time later, I can come back to this definition and give the full kind of combinatorial description. But the idea is that basically EG or IE, whichever is appropriate here, if I have a map from G to G prime in the graph minor category, this is equivalent to G prime being a minor of G. So interestingly enough, when we define these morphisms, we couldn't get them to go in the right direction. We had to make them go in the opposite direction. So a morphism from G to G prime is going to correspond to G prime being a minor of G. Hopefully that doesn't cause too much confusion. Okay, so the main theorem here, which we call the categorical graph minor theorem, and this is Miyata-Proudfoot and myself, is that, and basically, if M is a finitely generated G op module, the op here is just, the op here is just, again, because of this issue with the morphisms going the wrong way. So if M is a finitely generated G op module, then all of its submodules are as well. Okay, so in other words, in other language, like G-op modules satisfy an Noetherian property. And I call this the categorical graph minor theorem. Why is that? Well, so let me just very quickly as an example. So let's take M to be the trivial module. Which is to say M of G is just Z for all assignments. Well, if you take any set of graphs and you take the submodule generated by that set of graphs, it's going to have a finite set of generators, thereby a finite set of minimal things with respect to the graph minor order. So in particular, so any set of graphs must generate a finitely generated submodule, which implies the graph minor theorem. So this categorical graph minor theorem indeed implies the graph minor theorem. Not to say that I've provided a new proof of the graph minor theorem. The graph minor theorem goes in as input to the proof of the categorical version. So you can, well, as Nick says, like, we haven't reproven the graph minor theorem, but you should use this as evidence that this theorem is at least as deep as the graph minor theorem. That's the sales pitch version of this. Okay. Okay, so this is the categorical graph minor theorem. And so I'm going to spend the rest of today just talking about kind of implications of this.
Sure. Can I ask a question?
Yeah, question.
So first of all, on the theorem, this works for any Noetherian coefficient ring, is that right?
Yeah, that's right. Sorry. Okay. So I'm being a bit sloppy here. So I guess, yeah, so a G-op module where the coefficient ring is Noetherian.
And in your example, can you say that, like, the lattice of maybe monomial submodules of this M is the same as the like O set of graphs under the minor relation.
I think that's not like strictly true just because you have automorphisms. You need to like lift to a category that gets rid of those automorphisms, right? Like the standard like Grubner approach. Like this category is QG, and there's a Grubner category above it whose like morphisms exactly encode the graph minor theorem, and then you kind of push it down.
Okay.
Okay. Yeah. So, all right. So So as I said, the rest of the talk, I want to be showing kind of applications that we have for this, and also I want to talk about structural consequences within the category of within the graph minor category itself. So let me start there. So let me talk about structural. So, right, so, you know, when we talk about, say, FI modules, at this point we understand the structure theory of FI modules very, very well. The same is unfortunately not true of this graph minor category. It's all very new, and it feels like this category is considerably more difficult than, say, FI. But, so one question one might have, can we say anything about Hilbert series? Of GL modules? So, for instance, very famously, the Hilbert series of FI modules is rational, and in fact rational of a very particular form, which you can think of as telling you that this fact that FI modules, that the dimension growth of the graded pieces is eventually polynomial. But again, coming back up to this module, the trivial module, think about like, if you just did the most naive possible Hilbert series for a GOP module, then the trivial module would be the generating function for all graphs. So there's kind of a touch of like hopelessness there that this is going to work. But maybe there's a way to, instead of looking at the full Hilbert series, to restrict yourself in some way to make the problem more tractable. So consider the following. So let G0 be the subcategory of trees. Yeah. So because our graphs are connected, trees, you're not going to have deletions ever. So you can think of G0 as being the category of trees whose morphisms are contractions. Okay. Okay. So, well, it is a fact that if, rather, let me put it this way, there is a map, let's say W that go to T of W, which sends deep paths to trees. So there's a way to assign to every deep path a tree. That you can actually kind of see this quite nicely. So for instance, if my deep path is the following, something like this is a deep path. I can assign to this a tree in the following way. Just think about every time you read, so read from left to right, and every time you read a left parenthesis, you go up, and every time you read a right parenthesis, you come back down. So from this deep path, I can do the following. So you start at a point, I see a left parenthesis, I go up. I see a left parenthesis, I go up. I see a right parenthesis, I go back down. I see a left parenthesis, I go up, and then down and down.
Hey, Eric?
Yeah.
Could you just say what a deep path is?
Oh, yeah, sorry about that. So a deep path, you can think of just, well, just think about like the catalog numbers essentially. So a deep path is a word comprised of left parentheses and right parentheses in such a way that at no point do you have more right parentheses than left parentheses. And basically by the end, they even out entirely. Yeah, okay. So in other words, there's a way to assign to these deep paths a tree. This kind of assignment is surjective. Every tree will arise in this way. If you take your favorite tree, just fix a point to essentially be your root, and then just kind of chart that up and down motion. But, well, it's not going to be bijective because the same multiple deep paths can give you the same tree depending on what choice of root that you make. But at the very least, you have a surjective assignment here. So here's a theorem. This one is for myself. So if M is a finitely generated G-op module, or G0 module. So remember here now I'm restricting myself to only worrying about trees. So I'm looking at this subcategory inside of my bigger category. Then what I call the Hilbert-Dieck series, so HT of T equals, so this is going to be the sum over all Dieck paths of the dimension of M of TW times your kind of variable to the, how do I want to write this? The number of edges of T of W. Okay, so this sum here, this is a sum over T paths. So this Hilbert series is algebraic. So what does this mean? This means, well, if you think of it like, it solves a polynomial equation whose coefficients are rational functions. So as I said before, for FI, you have this rationality result. In fact, a bit stronger than rationality. It's rational with the denominator being like a 1 minus t to the n type of situation. So this is kind of the next step up in generality, algebraic generating functions. They're still quite nice. They imply certain things, but yeah, they're a bit more hard to maybe wrap your head around. But yeah, so again, here's a situation where instead of looking at the most obvious definition of a Hilbert series, I work with this kind of combinatorially coarsened version of the Hilbert series. Jordan, I think those are your kids. Okay. Okay. So yeah, so this combinatorial coarsened version of the Hilbert series, and we receive this, or we get this nice result. Yeah, so let's look at an example of this. We can actually see it explicitly, at least in one case. So let's say M, again, is the trivial module. So this is the module that assigns whatever your vector space to every tree. So what is the Hilbert-Dieck series in this case? So this is going to be the sum over Dieck paths of the dimension of the module. Of course, the module is trivial in each degree, so this is just 1. Okay. But this, as you can see, is just the generating function for the number of Dieck paths of, let's see.
There is a question in the chat.
Oh, I'm sorry. I wasn't checking chat. Let's see.
We should read them out loud because people watching.
Sure. So Jordan asked what a deep path was. I'm not sure if that was before or after I explained it.
That was yeah, answered that. So he was asking what happens if you sum over just trees instead of using deep paths.
Right. So Jordan, again, my go-to, like, is this going to work? Is just to plug in the trivial module and see if that's impossible already. So if you plug in the trivial, if you just try to do it, again, the naive Hilbert series, where you sum over, let's say, dimension of MOT times t to the number of edges or something like that, what you're getting is the generating function for trees, which is like a famously complex object. So again, this kind of illustrates why, like, I'm looking at these combinatorial coarsenings of these objects, is because, like, the objects themselves might be a bit out of our reach. Yeah. Right. So yeah. So let me finish this computation before I answer your second question, Jordan. So this thing becomes the generating function for the number of deep paths of length twice n, and of course, famously, that is the Catalan numbers. So this theorem is like a generalization of this very well-known fact that the generating function of the Catalan numbers is algebraic. Right. But yeah. Okay. So this is what I have to say with regards to kind of Hilbert series in this category. Again, it's still very much wide open. Like, we really don't know how to treat any case even outside of trees, really. So yeah, so this is an interesting avenue because, well, yeah. Sorry, I'm getting a bit rambly here, but remember, these Hilbert series are supposed to encode growth, right? Here's an example of a geob module, just to kind of layer on how difficult this is. An example of a geob module where to every graph you assign the vector space whose bases are indexed by spanning trees of your graph. Okay, so even just looking at how it's growing for the complete graph, I mean, Cayley's tree theorem is telling you it's growing like n to the n. So like in terms of like growth patterns and stuff like that, like these modules can get quite complicated. So yeah. At the same time, though, at least hopefully this result shows that if you allow yourself to coarsen your definition of Hilbert series a bit, that there might be something there.
Can I ask one more question?
Yeah.
So this Catalan example is like square root 1 minus 4t squared or something.
Something like that, yeah.
Yeah. Do you know an example where you get something algebraic that's like worse than square root?
That is a great question. That's a great question. Actually, my impression is that the answer is going to be no. I think square root is going to be the worst that you.
Oh, okay.
Because like somehow, I mean, this theorem is coming from the kind of lingual stuff, and so the languages that you're encoding these morphisms as are just like decorated deep paths. It's like deep paths with certain decorations on them. So. It wouldn't surprise me if the answer was that square roots were the worst case. Okay. Yeah. Thank you for that question. Okay. Okay. So just very briefly, one more structural concern that I want to talk about, and this one is for the topologists in the building. So. Another structural kind of concern. So another interesting subcategory is what I'm going to call G with a little subscript G and an upper RED. So this is the subcategory of graphs with first Betti number equal to G, and no vertices of degree 1 or 2. So the RED is short for reduced. For those who have studied, say, outer space, you've probably heard about reduced graphs before. Or for people who do like the Chan, Galateas, Payne stuff, the moduli space of tropical curves, working with reduced graphs is something that's quite natural and quite important. But yeah, so this is the subcategory now. I'm looking at graphs whose genus or first Betti number is fixed, it's G, and whose has no vertices of degrees 1 or 2. Okay, so I mentioned outer space before, and for those of you who have seen that construction, you might kind of guess that there's some relationship here. And indeed, we have the following theorem. If you look at the nerve of the category GG reduced, this thing is a k pi 1 with pi 1 being out Fn, or out Fg. In particular, the nerve of this category is a classifying space for the auto-automorphism group. When you work with Color-Voltman outer space, one of the first things that you learn is that, in fact, the action of the auto-automorphism group on that space is not free. It has finite stabilizers. In particular, like Color-Voltman outer space and the quotient by the auto-automorphism group is only telling you things about the rational homology of out Fn. The nerve here, though, actually gets at the full thing. So this is like a full-on classifying space for this group. In particular, like one way to think about this nerve is you take Color-Voltman outer space. When you define Color-Voltman outer space, you have this like equivalence relation on graphs that you impose. And so what we do is we get rid of that equivalence relation, which in effect creates these infinite dimensional pockets at every point. And because you've added this infinite dimensionality, you reclaim freeness of the action. Yeah. So again, here's a very natural subcategory of our category, which has this really nice kind of topology to it in a sense. It's a really nice structure. I'm really just kind of throwing all this stuff out there to stress that we understand, in fact, very little about this big graph minor category. But at the same time, it has so much stuff packed into it. Yeah, Jordan?
Can I understand? So if we're fixing that first Betti number,
yeah.
Maybe you said this, I just want to understand, then we're not really deleting, right? Then we're only
contracting, that's right. So that's a consequence, yes.
I do feel like it somehow has a different flavor. Like I feel like in the FI language, I feel like it's like if there was no downward maps and we were like, there's a group to it, right? It would be like FI, but like the species thing where there's only the permutations, but not the downward facing maps.
That's right.
It has a very different flavor in some sense.
So that's right. So somehow one way to visualize the graph minor category is you have these stratum, which are basically the first Betti number, and the contractions are going only left and right, and the deletions are going kind of up and down. And so you have these stratum, and each one of these stratum are really have beautiful topology and interesting facts. And we don't really understand how the deletions are allowing these things to glue together.
I mean, do you think it's possible that this category is, so to speak, the right way to stitch together the out FNs for various?
Again, it's super possible. We haven't studied it enough to say for sure.
Okay, I won't press, yeah.
Sorry about that. Okay, anyways, so I'm throwing all these structural results at you just to stress that A, we really don't understand the full graph minor category, but B, that within the graph minor category, there's all this beautiful structure that we can prove. And so I'm just doing this as kind of a sales pitch that there's quite a lot to be done here, and it seems like it's heading in a very interesting direction, at least to me. Okay. All right, so that's all I wanted to talk about structurally. The next thing I want to get to are applications. Yeah, so let's. Okay, so okay, so as the title of the talk suggested, our primary application of the Noetherianity of, or this categorical graph minor theorem is related to graph configuration spaces. So let me just write down a definition here. So we write F N G to denote the unordered configuration space of G. Okay, so one of the earliest actually projects that that Jordan assigned to me as a graduate student asked like whether or not graph configuration spaces had any kind of homological or representation stability.
I never assign, I only suggest.
Yeah, that's fair. Jordan strongly suggested that I think about this problem. And indeed, so it turned out that they do not have homological stability. The Betty numbers of these spaces will grow and continue to grow. But they kind of have maybe one step removed from full homological stability. It turns out that there are maps which allow you to introduce points onto any edge of the graph. And if you act by all of these, and you need all of them for every edge, that you get a kind of stability with respect to like all of the maps at once. And in particular, you have a polynomial ring with multiple variables acting on the homology. And you get a finite generation result there. Now, one of the most interesting things that was observed early on about these spaces, though, is that not only are there natural ways to vary the number of points, i.e. introduce a point on an edge, but you can also naturally change the graph itself while fixing the number of points that are being configured. So this is a behavior that's somewhat unique in these parts. So our goal is to answer the question of what stability is observed if you fix N and vary G. So this research program has kind of a long history, like 5 years or so, where I was just like coming up with new ways to vary the graph. And ultimately, all of these results are, in fact, secretly special cases of the main result that I'm going to get to. But, right, so normal homological stability is concerned with what happens in configuration space if I vary the number of points, what stability happens. Here I want to argue that, in fact, there's an orthogonal question in the case of graphs, which is what happens if you fix the amount of the points that are being configured, but allow the graph itself to vary in some nice family. So, theorem. One kind of motivating theorem, this is due to Cullen Park, one kind of motivating theorem, which is really quite beautiful, is that the group H1 of F2 of G is torsion-free if and only if G is planar. So this is a theorem, as I said, of Cohen-Park from the mid-2000s. And again, we see this condition of planarity, this minor closed condition of planarity. And what it says is, again, I fix the number of points. I'm only configuring 2 points. But if I allow my graph to vary within the planar graphs, we observe that everything you get is always torsion-free. And in fact, conversely, if you took something that was non-planar, that you would find torsion in H1 of F2. Okay. So this is kind of a uniformity result in a strong sense of how the torsion is acting across all graphs. Right. So in fact, just as the kind of Kuratowski-Wagner was a special case of the graph minor theorem, I'm going to claim that this is a special case of the categorical graph minor theorem, or a consequence of the categorical graph minor theorem. And so the theorem, this is Miyata, Proudfoot and myself. Is that the assignment? Oh, so let me start from the beginning here. For any fixed I and N, the assignment where you send G to the ith homology of Fn of G. So right now, this is just assigning a graph to a group. In fact, you can enhance this, can be enhanced or equipped with the structure of a finitely generated G-out module. So I want to stress, before I even get to consequences of this fact, I want to stress the fact that the morphisms in this category are inducing things on these homology groups is very non-obvious. That itself, just the fact that there's a structure of a G-out module, period, forget finite generation, the structure of the G-out module itself is actually not obvious here. Remember, part of the G-out morphisms are contractions, and you would expect that contractions don't play well with configuration spaces. You're causing collisions of points. But in fact, there's a way to do it. That's homotopically consistent. And this is, so I guess I can say that these morphisms were observed to exist just at the level of homology by this group of Androm and Colin-Knudsen. Recently, Nir Gadish, Dane Miyata, and Maya Banks, and et al. There's another co-author, I apologize, I'm forgetting the name, but they actually constructed these maps at the level of homotopy. In any case, I just do want to stress that the fact that a G-out module structure exists, period, is non-obvious here. But on top of that, that G-out module structure is in fact finitely generated. So put another way, if you look at graph configuration spaces, there is some mysterious, for any fixed homological degree and any fixed number of points, there's some mysterious master collection of graphs whose behaviors are dictating how every other graph has to behave. Okay? So one corollary to this is that, in fact, the exponent of the homology group here only depends on, let me say at most, I and so So at worst, if you look at all of these homology groups, the exponent is going to depend on, at worst, I and N. So Phil asked a question, is the existence of this geomodular structure related to the fact that the compactly supported cohomology of configuration space is the reduced cohomology of Gn minus delta, where delta is the big diagonal? So not exactly, no, Phil. Right, so, well, okay. That fact tells you that contractions are inducing maps on compactly supported cohomology. But this particular fact that you get it on homology proper, I don't think you can use that route exactly. Yeah. Yeah, it's a different approach. Yeah. But yeah, so the exponent of these groups. So coming back to this theorem of Cohen-Park, so the group is torsion free if and only if G is planar. The full version of this theorem says that, in fact, the only torsion that ever appears in H1 of F2 is 2 torsion. So the theorem, the full theorem, says that if you're torsion free if and only if you're planar. Moreover, if you're non-planar, then the torsion that you get is always 2 torsion. So this you can think of as a shadow of the fact that, in fact, torsion in general, the exponent is being completely restricted by this finite generation result. Okay. Now, I said here at most. So earlier I had mentioned that introduce a point on an edge is giving you a way to approximate stability when you vary points. And this result tells me the orthogonal answer of if I fix the number of points and I vary the graph, that I get a stability. And so it's very natural to ask, can these two orthogonal versions of stability be made compatible with one another? And in fact, the answer is yes. Though the kind of technical aspects of that are a bit much for a minute. So I'm not going to get into it, but I can answer questions about it afterwards. So let me just say, in fact, we can get rid of this N dependence. Basically, all that I'm saying is like we can actually get rid of the N dependence. So for graph configuration spaces, for any number of points, the ith homology, the kinds of torsion which appear in HI are only depend on I. Okay, yeah, so yeah, I guess that's 50 minutes. So I'll just, for the most part, end here. Let me just end by saying that myself and Dane are also currently working on applications to these kind of classical topological combinatorics objects like matching complexes, flag complexes, and you get kind of finite generation results across graphs for all of these homology groups as well, coming from what's essentially the graph minor theorem. Yeah. So yeah, so let me just end it there. Thank you.
All right, thanks a lot, Eric. So are there any additional questions? You can either just speak up or type in the chat.
Eric, can I ask, going back to this question of what Hilbert series might mean while we're just kind of shooting the breeze, I mean, I have no sense of like what the right weighting would be that would correspond to the Dyke paths that you use for trees, but do you think it makes sense to sum against like the Tut polynomial of the graph? Because that behaves well with respect to the action. I mean, tree, that is number of edges or something with some modification to that. So I mean, you could imagine that maybe that kind of 2 variable gadget would be a way to, you know, if you have some module and you track its dimension on every graph, you could sum that against the Tut polynomial and get like kind of generating function that you might hope to have some properties.
Right.
What do you think?
Yeah. So I've considered things like this. So again, if you look at the Chan-Galateus Wood stuff, or Wood Chan-Galateus Payne, sorry. They work with generating functions for graphs, which they call orbifold sums. So in their context, first of all, they fix the first Betti number always. They only worry about contractions. So they fix the first Betti number, and they consider sums of things that look like a sum, and then you take like you kind of weight by the size of the automorphism group. And then you sum t to the number of edges. Something like this. And yeah, so the weighting is by the number of automorphisms of the graph. And so, maybe you could consider summing over both the first Betti number and the number of edges. Because if I know these two pieces of data, I can also recover the vertices, for instance. Because your Tut polynomial example would be, you would be summing over vertices and edges. And so this is essentially doing the same thing. If you sum over genus and edges, you can recover uniquely vertices from that. So yeah, some like orbifold thing, and then z to the genus or something like that. I've considered these things and I've spoken to them about it, and it's in progress. I mean, this is all very difficult combinatorics. So, but yeah, I'm really open to any suggestions of things that might work.
As Eric said, the top polynomial of a tree just recovers the number of edges. So it's not a subtle enough weight to pass the trivial module test. Like if you take the trivial module and sum over trees weighted by the top polynomial, you won't get anything nice.
I guess I'm not thinking of that as like the weights, but as like the thing that makes the sequence into a generator.
Yeah, but all the LSS do it.
Yeah, so sorry, could you then elaborate on that a bit more? I'm not sure I'm understanding what you're saying, Jordan.
Oh, I guess I just mean like in the tree example, I mean, you are doing some weighted sum of trees with some weights against the top polynomial. It's just that as somebody who it was like, the top polynomial of a tree is just t to the number of edges. So I guess I'm saying, I'll type it in the chat. You can imagine
I see.
some sum of dimension of m of g against some weight of g, which would be like the number of Dyke paths against tut of g. And it would be the tut that would give you like a t and a u, and then you would get some function of t and u. Which
I see. So like as your variable in the generating function, you take a tut.
Yeah, exactly. The tut is where the variables would come from.
I see. That's interesting.
I'm speculating that would be a form of it, just because the tut polynomial is sort of a universal thing that behaves well under these exact moves.
Right. Yeah. That's a great point. I haven't considered that.
What is a Tut polynomial?
As Jordan said, it's like the universal polynomial, which
it's like a thing whose definition I can't remember, but it satisfies some recursion relation exactly under deletions and contractions, and it's sort of the universal polynomial for things which satisfy such a recursion. And you can read off lots of other graph theoretic invariants from it, like can't you read the chromatic polynomial off of it or something, if I remember correctly?
Yeah, so any object which satisfies the deletion contraction relation is a specialization of Tut.
Are there any other questions?
I have a question. Oh, other people can go first though.
So you mentioned this theorem of Cohen-Park saying we have the specific homology group of the specific configuration space, which is related to planarity.
Right.
And planarity is this case where we have two specific forbidden minors that characterize it. Are there other examples of particular homology groups of particular configuration spaces or other naturally occurring geop modules for which we actually know what generating graphs are?
Right, so that's a great question with multiple parts. So there was a paper recently by N and Knudsen where they explicitly computed H2 for planar graphs. And it turns out that in that case, so somehow for H1, we actually understand this. The graphs you need to generate are the graphs that look like this, as well as a loop. Okay. Where you might say, wait, isn't this an infinite collection because I allow the number of edges here to be whatever? But the point is like the number of edges you need is never more than the number of points you have. So if you fix the number of points, then you get like this finite list. But morally speaking, these are the things that are generating H1. For H2, if you restrict to planar graphs, you're essentially looking at stuff that looks like this. And then like two of these next to each other like this. So like basically the natural lifts of these two things. But then you also have these things called theta classes, which are coming from the graph that looks like this for H2. And this is actually like a beautiful, beautiful result, which was observed in the early 2000s by Greist and Aaron Abrams, which is that if you look at configurations, I believe, of 2 points on K5, that it has the homotopy type of a surface of genus like 13. So there are these non-torus classes in H2. And in fact, like it's basically, yeah, anyways, there's topology here, but outside of these two examples, so in terms of torsion, no. In fact, it's a great open problem to detect torsion that's not two torsion. We do not know whether non-two torsion exists in these spaces. Yeah, as I said, it's kind of a big open problem. In terms of the generating graphs, we do know a little bit, but for the most part, no, we also do not really know what's happening, especially above H2. We have no idea. Okay. So I guess I should say the finite generation result here is really an Ethereum property thing. It's like, you encode the homology as a subquotient of some complex whose chains are finitely generated. And then by the Noetherian property, you can conclude finite generation, but it doesn't really get you closer to actually getting those generators. So that's another kind of open problem.
Well, and the original graph minor theorem is particularly usable all the time either in that way.
Yeah.
So that makes sense.
That's right.
And Jenny, did you have one more question?
Oh, yes. I wanted to ask, Eric, you mentioned early on that there are some subtleties in terms of defining the morphisms in the category.
Sure, yeah.
I wonder if you could expand on that.
Yeah. So we're trying to define morphisms that generalize this graph minor order. So let me just write it down real quick, and hopefully I can. So a minor morphism is a map phi. So phi goes from, let's say, G to G prime, and it's going to go from the vertices of G union the edges of G union the empty set, essentially, or like a void symbol, to the same thing for G prime. And it satisfies the following conditions. First of all, if you take phi and apply to the vertices, that this is just going to give you the vertices of G prime. So this says that vertices are mapping to vertices and that it's surjective in that respect. Number two is that if phi of an edge is equal to a vertex, or phi of an edge is equal to another edge, then the endpoints of E kind of do what you expect them to do. Right. So what I mean here is like if an edge is being contracted, then you expect the endpoints to like map to that common vertex. And if an edge is just mapping to an edge, you expect like adjacency to be preserved, right? So the vertices here should map to the vertices here. Right. The third condition is that if you look at the preimage of any point, that this is always a tree. So this is just the fact that like contraction should only ever be contracting subtrees. You shouldn't be able to contract loops, i.e. contraction should be homotopy equivalences. And number four is a bit more technical, but if you look at what phi is doing, if you look at what phi is doing when restricted to the preimage that this is a bijection. So this last condition especially might seem technical. What this is saying is that, for instance, here's an example. This thing has the following minor. And what this last condition is saying is if you look at the edges of the minor, of the smaller object, they should naturally embed into the edges of the bigger object. So in this case, right, it's like the edges here have kind of natural corresponding edges in the bigger object. So if you restrict your minor morphism to those edges which are mapping to edges, this thing is a bijection. Anyways, yeah, so as I said, it's a bit technical and combinatorial, but I can promise you if you work with this for a bit, it is really encoding the notion of a minor. The idea, again, an edge that maps to a vertex is being contracted. An edge that maps to this empty set symbol is being deleted. Vertices are going to vertices, and etc.
Okay. So let me just say two more things now at the end. So first of all, we're going to have just kind of hang out for a little while. I just put a link in the chat to another Zoom room. So we're going to just head over there and chat. Feel free to join us for however long you want, if you want to. Eric will be there and we can have some more questions. And secondly, I just want to remind everyone that the next talk is on October 9th and Jeremy Miller will be speaking. So mark your calendar. We'll send out an email the day before, but you probably won't hear from us until then. Okay, so I hope to see everyone then.
Thank you all again.
Thanks again.